In this problem, we're asked to design a compact tension specimen. Compact tension specimens are used to determine fatigue properties or fracture properties of materials. ASTM's standard E647 provides some guidelines for geometry of such a compact tension specimen. It doesn't give exact dimensions, but it gives ratios of dimensions. So we can see here we have W defined, and then everything, well, other dimensions are provided relative to W. So we can see here the height of the sample is related to W, and then the total width of the sample is also related to W. Now A is an independent parameter, which is the distance from the applied load to the crack tip. But we have to keep in mind that A must be greater than 0.2 times W, or the geometry is not considered valid. The other dimension that we have to play with is the width, which is defined by B. So in this problem, we're given a material. It's aluminum 7075 T654 T651 with a fracture toughness of 22.8 KSI inches square root. And we're asked to design a specimen that at a load of 4,000 pounds that the sample will equal its fracture toughness. In other words, it'll fracture. And in the ASTM standard, we're given the relationship of the stress intensity factor in mode 1, which this specimen is initiates mode 1 fracture in tension. And so we're given this relationship as a function of A over W, the load, and B, the width. So for this problem, what we need to find is K1 equal to K1C, and identify all the geometry for a load equal to P 4,000 pounds. What does W equal? What does B equal? And what does A equal? So there are multiple solutions to this problem. And to do this, I used MATLAB, as I thought it would be a more efficient way of executing this equation many times. So we'll switch over to MATLAB now. So here we are in MATLAB, which I'm using to design this compact tension specimen geometry. And I went about it two ways. The first way was to plot the difference between KIC and KI calculated for various parameters, and then looking at the plot, deciding on what parameters would work. The second way, I just picked specific dimensions and then solved for W. So we'll go through the first one, the first technique. So KIC is defined as the value that was given in the problem, 22,800, and the load was 4,000, which is right there. Now the width, we could let it be anything. And I took some trial and error to come down to 0.3 inches. But technically the width could be anything. And then the parameter that I wanted to vary was W. So I created a vector array that goes between 5 and 12 in 0.5 increments. And then the next parameter which I varied is the crack length. And I looked at 3 different crack lengths. A crack length of 3 inches, then 2 inches, and 1 inch. And I made a plot of each one of those. And the plot I made by solving for K1, the stress intensity factor, using the equation that was given in the problem and in the ASTM standard. And we can see the equation is quite long. That's the main reason I use MATLAB. So remember with MATLAB, when you have a vector and you're taking that vector to a certain power, or you're multiplying it by another vector, that you need to put a dot in front of the multiplication or in front of the exponent. Otherwise, MATLAB assumes that you're doing linear algebra type multiplications and gives you an error typically. So when I calculate K1, the next thing that I have is delta. Now the delta is my value of K1C, which was the given fracture strength of 22800, and I'm subtracting off this value of K1 that I'm trying to find. So if delta is 0, that means that I've satisfied the equation and it's found a W that I want. So then I plot W versus delta, and I do this 3 times for 3 different crack lengths, 3, 2, and 1. And I make myself a legend. So let's run this and show what it provides. Okay, let's run the program and see what we get. So we're plotting the delta value, or the difference between the critical and the stress intensity factor versus the parameter W for the compact tension specimen. So where each of these curves cross the y-axis at 0 corresponds with the solution that works, that would result in fracture of the specimen. So the 1 inch crack length, roughly 9 inch parameter W works, and the same for a 2 inch crack, and then a 3 inch crack need a slightly bigger specimen for this to work. It would be at a W of 11 inches. So any of those solutions would work. Let's go on to the second way that I solve this. I'll uncomment this. So in this solution, I am using the command VPA solve. What VPA solve allows you to do is to define a symbol variable in which I use the parameter W, and then we can give it an equation. So this is the equation for the stress intensity factor, and I then ask it to solve that equation On the right hand side, I state the symbol that I'm solving for and then give it some initial value. Typically isn't particularly sensitive to what value you put here. Alright, so one of the quirky things about VPA solve is that the output is here, and I assigned it to the variable WS, and WS has the type symbol, so you have to cast that into a double with this command. And I set that equal to WP, so now WP I can use just as any other double variable. And I print out W, B, and A corresponding to the particular solution I found. But I wanted to check if 0.2W is less than A or not. So to do that, I first print out 0.2 times W, but then I ask whether or not A is greater than 0.2 times W, and if it is, I give a true. If it's not, I assign this variable T or F to false, and then I print that variable out. So let's solve this first for A equals 3, so a crack length of 3. We'll get rid of this plot. So you can see our solution was 10.8, and for W, B equals 0.3, A equals 3.0, and then our 0.2 times W is 2.2, which is greater, which A is greater than that. So we're in good shape there. So now let's solve it for A equals to 2. And get rid of the plot. So here we obtain W equals to 9.3. And again, 0.2 times W is less than A. So that's true. So that is a valid solution. Now let's try A equal to 1. So W is 9.5 and 0.2W is 1.9, which is greater than our value of A, which was 1 inch. So therefore this is not a valid geometry.